All right, everyone, welcome back to the Synthesis Workshop podcast. Today, I'm delighted to be joined by Professor Sharon Neufeldt, who I'll now be calling Sharon, but had to get the formalities out of the way for everyone listening here. Really excited to have her on today because, your type of research is particularly of interest for me, who kind of studies a lot of palladium catalysis and really understanding, kind of going back to the drawing board, I guess, and some elementary steps of these palladium catalyzed reactions is something that I'm interested in. And hopefully, today for the viewers that we can get a little bit more insight to that. But today, before we get out into that, we'll start with, a little introduction about yourself. I'm reading your bio right now on your website, which I encourage people to go and do to learn about PIs that they are, moderately interested in. But grew up in Arizona, Tucson.
That's right.
And,
Yep.
I don't know if you want to tell us, a little bit about growing up in, I never really been out to is it still considered
Southwest?
Midwest, the West, Southwest? Yeah, that's actually,
Southwest. Yeah.
Yeah, Southwest. I don't know if you want to tell us, kind of coming up through elementary, middle school, high school, any activities, hobbies, and maybe just the general feel for Tucson.
Yeah. Well, Tucson is hot, but it's a dry heat. That was apparently almost like the state slogan. It's a dry heat. Yeah, I grew up, let's see, a little bit of a different background. I was homeschooled up until around 7th grade. I didn't really go to elementary school. I was homeschooled with my siblings by my mom. Let's see. I don't know what you want to know about what it's like in Tucson.
Maybe just
rattlesnakes,
anything.
Scorpions.
Let's go. Is it? Do you often find scorpions and rattlesnakes near the city? Is that true? I've heard this from other people.
That is true. I mean, when I was a kid, we used to live towards the middle of town, and then when I was a kid, like probably around 10 or so, we moved to sort of the outskirts of town. Where there's a lot more sort of wild desert around. And yes, my dad would regularly catch rattlesnakes from our yard. When he would find rattlesnakes, he would dispose of them. Aren't they like really dangerous? They are. That's why he would dispose of them. He didn't want them biting us, when we're outside playing or whatever. Them. Yeah. He would catch them.
Oh, maybe there's a safe way to catch them then. Okay, maybe there's a safe way to catch them. I'm just imagining someone like grabbing them by his hands. Okay, I'm just imagining someone grabbing by his hands. No, I'm sure there's definitely a much more safe way to do it.
You use a long stick, ideally sort of forked at the end. I mean, snake handlers have sort of like a curved stick, I think, or maybe L-shaped. But yeah, you just grab a long stick and use it to sort of pin it down by the back of the neck. I've never done it personally, but I've seen my dad do it. And then while you've got it pinned down, your shirt can't like move its head. You carefully reach down with your other hand and sort of grab it right behind its jaws where it can't whip around and bite you. And then my dad would
crazy.
He might. I don't remember everything he would do. He would at least just toss it really far away, like if we saw it on the trail. But there's also like gopher snakes, which look the same, and those are not poisonous or venomous. So my dad was very careful not to hurt.
So rattlesnakes are poisonous.
Yeah. Oh yes, venomous.
Okay.
Yeah.
That's really okay. Oh geez. Well, I'm glad I don't really encounter them around here, coming from the Northeast, or growing up, I should say. But I guess also coming up through, because you also did your undergrad at North Arizona State University. What I'm curious to know is like, any initial interest in STEM and kind of when those, interests began, and then did you enter in university as kind of a chemistry undergrad major, or kind of how this kind of trajectory begin?
Yeah. Let's see. So, I mean, like I said, I was homeschooled as a kid by my mom. My mom had a college degree in art, and always sort of preferred art. But I remember her teaching us some curricula that were like science-based things that I and my siblings always thought was really fun. But I don't remember having a particular STEM interest per se until probably high school. So my dad, he never finished college because he joined the military in the Vietnam War.
Sure.
but
Oh,
he would
wow.
always tell us like we should get a degree in science because then we can get good jobs, because he worked kind of a blue collar job. And my mom was a stay-at-home mom, and
That's
so he was
generally
like, yeah.
Sorry, I was just gonna say it's definitely
Go on.
the perspective of a lot of blue collar workers, like
Yeah.
go get a
Yeah.
job
I mean, he
or
always
go
had
get
an
a high paying job.
interest in the sciences. Yeah.
Right.
He had an interest in the sciences, I think. Like, before he joined the military, he wanted to study biology. I think he actually wanted to be a doctor, but then joined the military and went a different direction. But
Of course.
yeah, so he would tell us that we should get degrees in some kind of science because then we can get good jobs. There was always sort of an understanding that I and my siblings should go to college so we could get good jobs, and also that if we wanted to go to college, we would have to go on scholarships, which meant, have to get good grades and stuff. But yeah, I think in high school is about when I started getting interested in science. My dad actually gave me a book, The Hot Zone. Have you read it or
I have
heard of
not.
it?
No. Should I have? Should
You should
I
read it.
have? Okay. It's called The Hot Zone.
I don't know. Yeah, I think there was a movie made on it too. It's a Richard Preston
But it's
book,
a
and
book, though.
It's a book, although I think they made a movie out of it. But it's technically nonfiction, but it's written like a novel, and it's about sort of the discovery, I guess, of like Marburg and Ebola. So like that class of viruses.
Yeah,
and so
I'm looking at the Wikipedia now. I'm looking at the Wikipedia now for the book. So yeah, this sounds really interesting.
It's sort of like a science thriller kind of, because like, some of the heroes, I guess, of the book are virologists, epidemiologists, like working in BSL-4 labs at the CDC and stuff. And so I just thought it all sounded like very exciting. And so I was sort of interested in doing that, like becoming a virologist, I think, in high school. And around the same time, I took AP Chem at my high school when I was a sophomore. And the main thing I remember from that is it felt like the hardest class that I ever took in high school. Like I felt like I had to work the hardest in that class.
Right.
It still is,
I don't know
right?
why AP Chem is so dang hard. Like it's still so hard. I don't know why.
It was hard, and it was sort of a little strange. Like my high school was sort of like this kind of magnet high school where like by the time you get to junior year, all of your classes are AP classes. So like I think I took like 11 or so AP exams or something like that. But AP Chem was definitely the hardest one. Like I remember my teacher, Mr. Woon, on the first day of class, he gave us so these are students that had never taken any kind of chemistry before. So we don't know really what atoms are. I mean, but he gave us like a list of polyatomic ions, which I didn't really know what that meant. But it was like a couple dozen polyatomic ions. So, like phosphate or carbonate. So we had to memorize their names and their formulas by like later that week or something.
I hate that.
I also am not a big fan of memorization, but Mr. Woon was a funny guy. Like I think he did it to sort of, I remember a lot of students dropped the class or switched out into like regular chemistry after that. Like that first week. And I think he did it just to like
cut the wheat from the chaff.
Students out that didn't want to work really hard. Yeah, something like that.
I see.
He was a funny guy, but yeah, the class was like the hardest class to me, and we had a textbook. And I remember the textbook had one chapter in it on organic chemistry. I don't know the contents of that chapter though, because we skipped it because he said organic chemistry is really hard. Like that's what my teacher said, that was somebody that was fine with making us memorize all these like polyatomic ions on our first day of class. So that was my impression of organic chemistry, that it was really hard. And that's what I thought going into college. Yeah. Which is funny, but
I've like never heard this before. Like I've never like really heard this before that. Well, I guess you're probably the first person I've talked to where it's like you've actually got exposure, or I should say tangential exposure to organic, and your only impression was that it's really hard at like high school. So I can only imagine
Yep.
how that changes when you move to college, But
Yeah, I mean, kids these days are different. Like there's a high school student that's been like working in my lab the past year, and he's been doing amazing. And I'm like,
Wow.
when I was a high school student, I had no clue what like, yeah, I thought OChem was just something really hard. I had no clue about the concept of research, but yeah,
Right.
they're different
Right.
now. But
Yeah.
yeah, so when I went to NAU, uh, I went there because that's where, or in-state, I had in-state scholarships and stuff. So that's why I
Sure.
went to NAU. And I wanted to get away from the heat and the rattlesnakes and stuff. So um, that left Flagstaff as the place to go. Yeah, so I came in as a biochem major because I wanted to like they didn't have like virology as a major, but I felt like that was the closest. But because
Right.
I had taken AP Chem, NAU's policy, at least at the time, was like if you had a 5 or probably a 4 or 5 on the AP exam, then you would go straight into OChem in your freshman year. So I took OChem in my freshman year, which I was,
Hmm.
not super excited about at the beginning because my only impression was that it was really hard. But it turned out like I figured out pretty quickly that I absolutely loved it, like way more than I enjoyed AP
Right.
Chem, like general chem. And that was sort of how I ended up liking organic chemistry freshman year.
Yeah, I think for most students, like you really should. I mean, this is definitely true for pretty much all courses. Honestly, is kind of take opinions with a grain of salt as far as the coursework goes, because
Mm-hmm.
I was told the same thing about organic chemistry from, you know, generally the timeline is you have Gen Chem, freshman year, and then organic is the second year. Generally, for a lot of students. So, when you're a freshman, you kind of hear these opinions from upperclassmen who might have struggled in it because their end goals are to become, doctors, medical doctors,
Mm-hmm.
PT school, right? You get a lot of physical therapists, and in my case, I had a lot of chemical engineers, right? Because chemical engineers have to kind of take this class as well. So you kind of have a little bit of a biased opinion because it's like organic is like the very first time in a lot of students' life where you have to actually think outside the box. I think it's not everything's not told to you, and it's not all necessarily black and white. At least as far as STEM goes, right? I mean, we could have arbitrary talks in humanities, but I really do think that Orgo is the first like STEM course that really pushes you to think outside the box. So students generally don't really take well to that, and so my
Mm-hmm.
opinion is if you hear that organic is hard, just kind of take it with a grain of salt. I'd say because I obviously our opinions are a little bit biased now because we're in this field, but
Mm-hmm.
just go in with an open mind. I don't think it's as hard as people really make it out to be, but be prepared to really push yourself. I'd say that's my
Mm-hmm.
takeaway from Orgo. So I don't know if you
Yeah, I
agree
mean,
or
it's
disagree with
definitely,
that.
yeah, I mean, I think, there's some combination of like how well your instructor's teaching is a good fit for how you learn
Of
and like
course.
what your textbook
Yep.
is and
Yep.
stuff like that. But, I feel like if you go into OChem thinking like, feeling like in the past you've always gotten by with having like really good memorization skills. And there's always this rumor that
Yes.
OChem is so much memorization, which it sort of is, but like I feel like there's just so much more to it. Like you can't get by on just memorization skills because like there's so much sort of pattern recognition and sort of pattern seeking
Right.
skills that you need in there. And it's I mean, I think something I liked about the course when I took it as a freshman is like it's this interesting combination of sort of right brain and left brain thinking because
Mm.
like you've got your left brain sort of logic, like the logic of organic chemistry, but then there's this element of feeling like it's art, like drawing these swoopy arrows and getting your lines to be parallel and
Right.
like a cyclohexane chair conformation and stuff. So um yeah, so it's different. Yeah. And
Right.
I mean, different people will have different opinions, but I felt like it was easier than Gen Chem. um
Yeah.
maybe that it was
Same.
just sort of
Honestly,
like
same.
more to my taste or something, but yeah. um
Yeah.
yeah, so I
And
mean,
I'll never
and then
forget
I
like learning. I was to say, I never forget learning like retrosynthesis for the first time. Like that was such a weird
Yeah.
like I don't even know how to describe
Yeah.
that feeling learning retrosynthesis for the first time. Like thinking
Yeah.
backwards, like it was like a
Uh-huh.
revelation. It was like, oh my god.
Yes. And now like I feel like it makes so
Yeah.
much sense. Not
Yeah.
that I, do a lot of retrosynthesis myself, but like um yeah, like I remember
Sure.
thinking at the time, why do we need like a special arrow? Like why do we write this arrow in the back like in this direction? Why not just write our arrow backwards to show that we're thinking backwards or something, But yeah, it took a while to sort of adjust to that and feel like the convention made sense, but yeah,
Right. It's a well crafted arrow for us to specifically mean we're gonna think backwards. It's really well thought
exactly.
out.
Yeah.
Um
Yep.
so after did you do any like undergraduate research at NAU or you
Yeah,
kind of
I
stick
did.
to lecture?
So
Mm.
so during my freshman year, there was this guy that moved to NAU, that he used to be the president of Aldrich Chemical Company, and had retired.
Oh
So that
wow,
was
okay.
back when it was just Aldrich, like not Sigma Aldrich or Millipore. Um, and so he moved to NAU when he retired and like had a position there as like a research faculty. Like he had a little like one
Mm.
lab room, and he was sort of doing kind of like consulting work almost for Aldrich. Like he was trying to like basically do like sort of smaller scale process chemistry. Like he was developing like um, sort of routes, I guess, or processes for making like I think potassium organotrifluoroborate salts at the time. He was an H.C. Brown
Yeah,
like PhD
important.
student. So
Wow.
yeah, so really into boron compounds and stuff. And so
That's an important
everything
boron
he did
reagent,
was
so
like,
that's really important.
it is, yeah. And I
Extremely
remember
important.
like being told about him by like my OChem professor, like that he was looking for a student to work in his lab. NAU um, doesn't have like a PhD program in chemistry.
Yeah, sure.
So the only
Same
students were
with
like
my undergrad.
undergrads. Yeah.
Yeah.
So he was looking for like an undergrad to join his lab. And I remember somebody describing him like he's like a kid in a candy shop with all of like his Aldrich glassware. He's just like having so much fun, just like setting up these reactions. Like I'm sure he was somebody that like loved being a lab rat, I think, and was like happy to probably retire from sort of a more administrative side. But yeah, everything he did was
Right.
on like a huge scale, like, like 5 liter, 10 liter round bottom flasks with like overhead stirrers and stuff. Um, and so, yeah, so I started working in his lab like the summer after my freshman year. At first, it was just like helping him make these trifluoroborate salts. So, like, not really anything sort of like publishable. But after that,
Sure.
he kind of arranged for, I kept working with him the whole rest of the time I was there. I was the only student in his lab. After my sophomore year, he arranged for me like that summer after my sophomore year to go to UPenn to work in Gary Molander's lab, um,
Wow.
as like sort of a informal REU kind of thing. So I spent a summer
Yeah, yeah,
there
yeah.
in Philadelphia in the Molander lab. And that's where I sort of got the perspective on what it would be like to go to grad school. Um,
Yeah.
and then I came back in Dr. Lane's lab at NAU. We started working in a different area that was trying to make so like ammonia borane, like the NH3 BH3 adduct. So
Yeah.
like if
Hmm.
you take NH3 Lewis base and BH3 Lewis acid and combine them, you get this adduct that's a solid. And so especially then at the time, because this was kind of the early 2000s, or probably around 2006 or so, there is a lot of interest in these compounds for like hydrogen storage applications. And so Dr.
Okay.
Lane had like ended up getting this DOE grant, I think with
Oh
some
wow.
collaborators, to look at amine borane, like ammonia borane derivatives, like different amine boranes, because the idea was ammonia borane is a solid, which is
Hmm.
not the best for sort of density in terms of like if you want to have it like on board a vehicle or something as a hydrogen source.
Right.
So they wanted to get a liquid form of like ammonia borane. And so like I had this little project that was just making like different like alkylamine boranes, and like making different sort of combinations of these together with ammonia borane, like, you know, trying to take advantage of sort of melting point depression and like trying to get sort of a liquid formulation, which by the time I stopped working in his lab, like, you know, right before I graduated, the project was getting close to done. There was a lot of work with collaborators that needed to be done. Dr. Lane unfortunately passed away that summer after I graduated.
That's sad.
Which was, yeah, very sad. But yeah, but we ended up publishing, like, with the collaborator sort of took over, and we ended up publishing that work.
That's awesome.
So that was the research I did in undergrad.
That's really cool. How, like, I mean, it's crazy. Like, I mean, and you know, you could have never imagined that like a little undergraduate research could have like put you on this trajectory. You know what I'm saying? Like, even I still feel that way, and I feel like that's so true across everyone I've really talked to. Just kind of like it was just an initial interest, and I presume you like, you know, I guess you were told by some advisors to go like pursue undergraduate research, and like you kind of were like, okay. And I assume, did you reach out to Dr. Lane, or how did that kind of work out?
Yeah, I mean, I think I didn't reach out. No, I think it was my OChem professor, like my second semester of my freshman year, who was like, yeah, there's this new guy, Dr. Lane. He's looking for like a researcher to join his lab. You should talk to him. Like, you know, would you be interested in that?
Yeah.
If so, I'll put you in touch with him. And I was like, yeah, sure. Like, you know, zero concept of what research means. But
yeah.
like, yeah, whatever.
Same.
Like, yeah, and when I talked to Dr. Lane, he was like, yeah, you know, I can pay you like hourly or whatever over the summer. And I was like, whoa, I get paid? Like, you know, sounds good to
Right,
me.
it's so crazy.
Yeah.
Right. I'll never forget taking summer courses. It would have been summer 2018, and this is like when I was in, like a sophomore or going to junior, something like that. I forget, but yeah, I was living on campus, taking classes and doing research. Like, it was like one of the best summers of my life. Like, just hang out with my undergraduate advisor, who he didn't really come into the lab all that often. He wasn't really a lab rat because he was more on the admin side, but he was like super cool to just kind of, you know, I was an 18, 19-year-old just in lab doing stuff. Like, you know what I mean? Like, it was just really fun. And those early moments, man, like, I don't think they're so important for how you see chemistry and, like, you know, your future interests, you know, like, it's just so important. So I really just I cannot stress enough, probably, like, if you have even the slightest interest in research, like, just go ask, because it is such a unique experience. And even if you don't like it, at least you learn you didn't like it. So, but yeah, that's my opinion on it, I guess.
Yeah. Yeah, and I mean,
now,
thinking about that. Oh, go ahead.
Oh, go ahead. Go ahead. Sorry.
I was just going to say, like, you know, now as like a PI myself, like sometimes I have to sort of remind myself, because, you know, you interact with so many students on a daily basis. Like, it's easy to forget like what feels like just sort of, you know, passing interactions for you as a PI might be much more meaningful for the student, because you know, like, they only have one research advisor. So like, yeah, it's useful to sort of remember how much of an influence those experiences,
those little interactions are. Yeah, completely agree. Completely agree with that. Those little, because, yeah, I mean, obviously you're so impressionable, you know, you're so impressionable at a young age. So that those little interactions really make you feel, you know, special. And it really goes a long way. Now, so after undergrad, you know, you did your PhD with Professor Melanie Sanford at University of Michigan. Now, was graduate school like the next? I mean, you had mentioned you liked lab work, but was that kind of the natural progression? And, you know, what made you, you know, go to Michigan, and maybe some of the things leading you to join Melanie's lab?
Yeah, I mean, I feel like I always tell undergrads, like, don't go to grad school necessarily just because you feel like you don't know what else to do, because that might not, you know,
that's good advice.
Might not work out so well. But that is kind of what I did, and it was fine. Like, I just felt like like that was I don't know, it did just seem sort of like, oh, if you want to do something in chemistry, you go get a PhD in chemistry, kind of. Um, and yeah, so that, I don't know, but at least that's what Dr. Lane told me. Um, yeah, you should be thinking about going to grad school. So yeah, I mean, and I had no idea who anybody was in the field at all. I think I used like the US
Same.
News like rankings to come up with a list of schools to apply to. And then
That's
there
such a
was a
good list.
handful. So like, well, I had like a top 5 basically to apply to.
Sure.
It wasn't literally the top 5, but like I had picked 5 from, you know, the top 10 or 20 schools or something to apply to. And then there was like a smattering of like 2 or 3 other schools on there just because like some, like Dr. Lane suggested it to me. So Dr. Lane had suggested I add Michigan to my list because of Ed Vedes there, who he had a connection with. Which was a name I'd never heard of. But I was like, sure, Michigan, like, you know, Dr. Lane was from the Midwest, you know, he liked that. So I added that to my list, as well as other schools he had connections to, like Purdue and Iowa State. But yeah, so Michigan like wasn't one that I had sort of put on the list myself or come up with. So, you know, once I started getting like, you know, acceptances and stuff, I was deciding what schools to visit, you know, because a lot of the recruiting weekends sort of overlap and stuff. And I'd sort of picked like 5 schools I was going to visit, and I wasn't going to visit Michigan because I think it like their visiting weekends like conflicted with other schools I thought I would probably be more likely to attend. So I wasn't even going
Interesting.
to
Okay.
visit Michigan. But then I remember I was in lab and I got a phone call. It must have been like on my flip phone. Do we have flip phones? I don't know. Like I got a phone call on my cell phone. And it was this lady that was talking really fast, and she was telling me like, oh, I hope you're going to come to our recruiting visit. Like, she said she's from the University of Michigan, the chemistry department. She hoped I was going to come. You know, they're really excited about like me coming to visit and hope I can make the recruiting weekend, and like talking, I don't know, like she'd be happy to tell me about her research and her colleagues would be happy to as well, and blah, blah, blah. And it was going to be great. And like, she just sounded so genuine and excited, and she was talking really fast. I just felt too guilty to say no. Like, I felt too guilty to say like, no, I'm actually going to visit another different school. So I said
Oh
yes, I
man.
was going to visit because I felt guilted. I mean, she wasn't trying to guilt me, but that's how I felt. That person ended up being
Yeah.
Melanie Sanford that was calling me, as you might have
Yeah.
guessed by the talking fast part.
It-
And so I did go visit, and I think it was the last school I visited. um, and yeah, I just like, I wasn't expecting to like it particularly because I didn't know anything about it, and I didn't know who Melanie Sanford was or anybody. But yeah, when
How
I
would you?
visited it, it just to me just felt so much different from all the other places I visited. Like, you know, there were a couple of grad students in Melanie's lab that like made a real effort to like talk to me and stuff, Lopa and Deepa.
Yeah. Okay.
And and everybody just seemed so like excited and energetic and like happy and like really motivated and excited by chemistry and stuff. Like it for me, it felt like a different vibe than I was getting from some of the other places. And yeah,
Yeah.
so even though I still didn't know really who Melanie was, and I didn't know, like, I didn't understand her research, I just knew it sounded exciting, probably because she seemed excited about it and her students seemed excited about it. So you know, I mean, I'm skipping some details, but that's basically
Of
why I
course.
ended up going to Michigan, was to work with Melanie because I liked Melanie, and I liked sort of
Yeah.
the feel of her lab.
Yeah.
Yeah, so when I went to
That must be
Michigan,
so. That must be
go
like
on,
so
yeah.
cool. Like you, like getting a getting a phone call from Melanie Sanford is like. Well, you know, okay. A couple things though. It is interesting because, like, as an undergrad coming out, like you know, you went through your undergrad, but listen, graduate school is another level. Like, but it's like you're not supposed to like. There's no way of like knowing these people. Like, it's funny. It's just kind of
Right,
funny. Like to like undergrads and even just normal people in the world. Like these superstar, like no one knows who these superstar chemists are. No one knows who these chemists are, right? Except for the chemistry community. It's just
right,
kind of
yeah,
funny that way.
yeah,
Um, So that's really funny. You got a call. Now, was this in her early career? Like I don't know when she started, but I don't
Yeah,
know
so
like
this would
when.
have been this
Um,
would have been 2007. So she
okay.
was, I think she started 2003. So she was already like,
Yeah.
well on her way to being a superstar, I would say.
Yeah. That's really cool though.
If
Yeah.
not
I just
already considered to be a superstar, yeah.
right. I'm
Yeah,
sure.
I had
Like
no idea. I
obviously,
mean,
it's funny. Go ahead. Go ahead. Go ahead.
no, I was gonna say, like, I feel like if you are an undergrad doing, like, if you are at an R1 institution and you're in like like a lab with PhD students and stuff, you probably would hear these names more. Like, I know the undergrads in my
Right.
lab
Yeah.
definitely hear us mention names of, big players in the field and stuff, but the only ones I had
Yes.
heard of were like H.C. Brown and Gary Molander, basically. Like I didn't know names, but yeah.
I didn't know anyone. I literally didn't know anyone. In fact, when I applied to Houston, I didn't know like I applied to Houston because I liked the city. Not even I knew anything really about the chemistry department.
Huh.
Now,
Uh-huh.
it really worked out for me because I thought it'd be fun to live in Houston for my mid 20s. But I have a personality where I kind of would I would be able to fit in and get along with anyone. So it's like didn't really matter to me.
Hmm.
But I'm not suggesting this is what people should how they should select graduate school. But that's what worked for me. But yeah, the point is though is that like you're not like yeah, you're right. Unless you go to an R1 undergrad, you're not really going to know the big players in the field, and that's more than okay. In fact, I don't even really know like understanding their research. You don't have to pretend that you understand their research to like talk to them. Like it's like it's just not that's okay, right? So anyway,
Yeah.
I guess that's my
I
spiel
mean,
on
I
it. But
I think I
go ahead.
I mean, I also feel like it like it might feel like such a big decision. What school do you go to? Like, what grad school do you go to? What advisor do you work with? And like for me, in retrospect, I feel like it was like the most perfect way it could turn out for me to go work with Melanie Sanford.
Mm,
But in reality, I think it's important to note that like there's not actually just one like good path to take, so
right.
you feel like you ended up in a good place based on liking the city you were going to go to, and me because I got like a phone call kind of, but like there's probably many other ways I could have chosen what school to go to and have gone to a different school and been happy at other schools and stuff, and probably the same for you as well. So like I feel like for undergrads that are considering going to grad school, it might be useful to remember like you don't have to get it perfect. Like it's not like there's only one possible like soulmate path for you to
Yes.
take. Like there's probably lots of paths you could
Yes.
take that would be really great. So
Yes. That is absolutely the truth. There's not one perfect school. Um, yeah, and especially if you have a personality that's kind of more open minded, like which
mhm.
then you're like there's plenty of professors out there at different institutions that'll be great for you, and just because you don't go to like the top 3 schools in the nation does not mean that it's not like you're not any worth less. You know what I mean? So, um, yeah, that's my opinion on it. So yeah, those are definitely great points. But so you arrived to Michigan and you are doing, palladium-catalyzed CH functionalization. So I don't know if you want to tell us a little bit about, kind of maybe your project, but also maybe some of the key takeaways from your graduate study days.
um yeah, I mean, I worked on a few different projects. My two main ones kind of that I would say that I spent the most time on, or were the slowest projects,
Mm-hmm.
was so Melanie had already by then obviously sort of developed this like ligand directed palladium catalyzed CH functionalization, and so I had this
Mm-hmm.
project where the idea was like you can't use like ketones as directing groups, under these conditions, like they're not good enough directing groups, but they would be sort of more synthetically relevant than some of the directing groups that they looked at. So the idea was to sort of develop a transformable or removable directing group that could turn into a ketone,
Okay.
basically. So that ended up being O-acetyl oxime esters, as directing groups because you can sort of hydrolyze those back down to
Okay.
ketones afterwards. Not that easily, but yeah, so that was the first project I worked on. And then, although I don't think it was the first one that I like got published, or maybe like that one just felt like it took a while. And then, oh no, the project that took the longest that I felt like would never end was sort of a spin-off. Like one of the directing groups I had been testing in the first project was like O-allyl oxime ethers. And I had
Okay.
found that like the allyl group, like the alkene was getting dioxygenated. So like with iodobenzene diacetate, it was like getting diacetoxylated. So kind of difunctionalization of an alkene. And so that ended up being sort of a spin-off project to like use the nitrogen of the oxime ether to kind of direct this difunctionalization of the alkene in like an asymmetric way if the oxime is derived from a chiral ketone. And I was like, okay, like I remember there being a lot of interesting NMR spectra that I looked at and stuff like that. And then I got involved with some of the like photoredox stuff. So Deepa Kalyani, who was a 5th year student in the group when I started, she had graduated and done a postdoc with Scott Denmark. And then she came back.
What a guy.
Like briefly, she came back for like a summer or something, I think, before her job started. She was going to St. Olaf. And during that summer, she was doing research in Melanie's lab because she loved it there. And so she had started this like photoredox thing. Maybe she was there a whole semester, I don't remember. So she started this like merging palladium catalyzed CH functionalization with photoredox chemistry. I think, there's like a Rubipi photocatalyst in combination with aryl diazonium salt. So like you generate this aryl radical that then like reacts. You can get CH functionalization under much more mild conditions like CH aerylation. And so like she didn't quite finish the project before she left. And so like I ended up joining the project to sort of work out some reproducibility stuff. And then I started sort of doing a couple other projects kind of in the same area. But yeah, I mean, I think one thing in Melanie's group that was a little bit formative for me was actually Melanie asked me, she said, she was invited to write like a review like for accounts of chemical research on like site selective CH functionalization. She asked me if I wanted to write it. And I was like, yeah, I like writing. So I did that. And that felt like really formative because, at least in retrospect, it did. Because number one, I realized how much I like writing. And number two, because like that was the first time I encountered the term like catalyst controlled selectivity, because everything that I'd done in Melanie's lab, like selectivity was controlled by this directing group. So part of the substrate. So it was substrate controlled selectivity.
Right.
And so that concept of catalyst controlled selectivity was sort of in my mind, at least subconsciously, for a few years. And so like that's ended up being a lot of kind of the focus I'm doing in my independent research, not with CH functionalization, but in general, catalyst controlled selectivity. Yeah.
That's really cool. Yeah. Thanks for sharing that. That's really cool. One other thing though, too, is how did you adjust though to the Michigan winters coming from Arizona? Did you adjust well?
Yeah, well, I'd sort of already adjusted because my undergrad NAU is in Flagstaff. So you've never been to Flagstaff, like the Grand Canyon?
No, unfortunately. Okay.
You'll get out there sometime,
I didn't realize it was that
yeah.
close.
So
one day.
Flagstaff's at like 7,000 feet elevation, so they get snow and there's pine trees and stuff like that. So
okay.
I started to adjust to winters already at NAU.
Gotcha. Okay.
I mean, it's different in Michigan, but yeah.
Yeah, it's a different level in Michigan. But over in I haven't been to Ann Arbor, but when you're not doing chemistry, were there kind of things that you like to do up in Ann Arbor, or what was kind of the thing to? Obviously, you have the football team, I guess, but what were some of the things you'd like to do?
I got into running when I was in grad school. I never really did anything athletic before that. But I think my second year of grad school, I got into running. And so that was like my main sort of thing. I did a couple like half marathons and
Oh,
trained
wow. Okay.
for a marathon, and then I like injured my hip, and it still sort of
Dang.
causes problems to this day. But
Yeah.
yeah, that was the main thing I sort of did when I wasn't working in lab. And I told you I have
That's such
like that science blog already also, but those are my hobbies, I
we got to
guess.
bring it back. Bring back the science blog, please. We have to plug it here. We're going to plug here the science blog from Sharon. Maybe we'll leave a link in the
Nobody
description of the
reads
video. People go check
blogs
it out.
anymore.
Listen, we're gonna bring it back. It'll be good. We're gonna plug the blog in this video description. People can go read it. It's good that you say that you did running though, because that is I feel like a lot of graduate students neglect their physical and mental health in graduate school. Please, like, I'm telling you right now, chemistry is not the most important thing ever. If your physical and mental health are not in order, like, it's hard to do chemistry. I'll just put it that way. Get those in order and make sure you're good. Because it just makes sure my opinion is, if your mental health and you're working out, then your chemistry generally, like, it feels better. Whether or not it works, but like you just kind of feel better. So that's super important. And I don't say this lightly, like, really, really go make sure you have hobbies that are outside of it, and making sure that you're, drinking enough water and getting physical exercise. Because at the end of the day, like, those are the most, like, some of the important things you could do for yourself. So, yeah. So moving on then from graduate school, you did a postdoc with Ken Houk. So now we're kind of moving into computational chemistry here. I guess, you mentioned before that you began writing with Melanie, right? To write the review. So you already kind of have like writing, and of course the blog, which kind of goes into becoming a professor. But so at this point, were you really like considering going the academic route? Like, when did that kind of really enter your mind?
I would say I was considering it, but I didn't feel like I could. Like, I didn't feel like I actually could be successful at it, I guess. But I guess I felt like I probably wanted to go into some kind of academic career, but whether that would be sort of more teaching focused versus more on the research side, I remember I told Melanie, like, I didn't feel like I had the tools I need to like become an independent researcher. Like, I told her for a postdoc, what can I do that's like a really like complementary skill set, like because based on like like I liked what I did in grad school, but I didn't feel like, I don't know, like I didn't feel inspired, I guess, to be able to do something like that myself.
Right.
Or at least not confident enough. And so she was the one that had suggested working for Ken Houk, which when she told me that, I was like, I'm not a computer person. And she's like, well, hear me out. And like she kind of explained why she thought I would like it. And Melanie is a very insightful person, an intuitive person. So I think she was right. It turned out I did really like it. I really like the aspect of sort of almost being able to engineer your molecules and see what they're doing. And and I think I started realizing that what was really inspirational to me was understanding how things happened. So like mechanistic studies, rather than necessarily developing new methods. I mean, I think that can be an important outcome of mechanistic studies, is developing new methods. But what's really inspiring for me is feeling like kind of, a scientific detective, like trying to find the clues that will answer a mystery, answer a question of why something happens the way it does. And in Ken Houk's lab, the main project I worked on was like about site selectivity, again in CH functionalization, this time with iridium. But that this sort of site selectivity theme kept kind of coming back. And so during that time, I was simultaneously, it was this position called the Cram Teacher-Scholar position at UCLA, which was basically like 50% teaching and then 50% research. So like I taught a course every quarter that I was there, and then also like did research in Ken Houk's lab. So I was, I enjoyed both aspects, but I think the experience taught me that even though teaching is rewarding for me, it's not rewarding enough for that to be my primary focus, because there's something like, teaching always repeats itself. That's how I feel. Like you teach a class and you get towards the end of the class and you've seen the students sort of grow so much and learn so much, and then you just start all over again and they don't know anything. And you know what I mean? So I felt like to have the motivation to do that, I needed something else that was always moving forward and not just rolling back down the hill over and over again. So that was sort of when
really interesting perspective
started.
Yeah, I like that.
Yeah, I mean, it's sort of like work-life balance. I feel like there's a balance between teaching and research. Like to stay motivated in teaching, you also need, something else that keeps you balanced, and vice versa. So it was around there that I started feeling, and I was feeling sort of more inspired and excited about kind of my own ideas and stuff, based on kind of having this new set of skills, like doing DFT studies. So it was around then I decided that I would give it a try, applying for jobs and see how it went.
During your postdoc, were there any any key takeaways from the CH activation? Like, what were some of the maybe high level stuff?
So it was looking at site selectivity for this CH functionalization reaction of pyridines, where you have this amide at the 3 position of the pyridine. And so the amide can direct rhodium-catalyzed CH functionalization at either carbon 2 or at carbon 4, like either one is sort of ortho to the amide. And with the pyridines, you get really poor site selectivity, like kind of a mixture of the two products. But if you oxidize the pyridine to the N oxide, you get very high site selectivity for reaction at the position next to nitrogen, so the C2 position. And this was work that had been done by some people at Amgen. And so they wanted to collaborate with Houk to figure out where the selectivity was coming from. So that was kind of the project. And I mean, the explanation sort of is maybe not as straightforward as you might like it to be. The explanation was sort of like a combination of like increased acidity of the C2 position, but also like the part that I found the most interesting was there seemed to be a role of like these electrostatic interactions between kind of that really sort of partial positive area near that oxidized nitrogen and a portion of the catalyst. And another thing I kind of took away from that project, which I think it was something, maybe it made it into the manuscript, was like IRC calculations. These are calculations where you have a transition state and then you sort of follow it like effectively as it slides downhill in energy, either backwards or forward. And you kind of like watch how it, how the molecules sort of collapse back to the reactants or go forward to the products. And so I remember just thinking that was really interesting, sort of like comparing those IRCs for like different sort of, if you had a slightly different substrate or different reactant, and sort of being able to compare. I mean, it's sort of like how early or late the transition state is by like following that path. So yeah, there were just various aspects of it that I found like really sort of fun to try to like figure out. Yeah.
It is one other thing I'll say is that it is pretty crazy to see how many publications Ken Houk is on. That's like every time there's some of these DFT, it's like he's on it. It is It is
Yeah,
it is
he's like
I came in like, oh my God.
he's like the Kevin Bacon of organic chemistry. Like how many degrees of separation? Like everybody has like some type of association with him. Either they've collaborated with him, or they've collaborated with one of his students, or they
Yeah.
spent time in his lab or whatever. Like everybody has some kind of connection, like 2 degrees
It's
of separation or
crazy.
something. When I was in his lab, I think I don't remember if it was like 2014 or so, or 15. He hit the 1,000 publications milestone. It was a big
Wow.
celebration. And now
Yeah.
he's like,
I
I
bet
don't
it was a
know,
fun
he's
party.
up to like 1,500 or something. But yeah, he's quite
Jesus.
prolific.
That is so cool. Um, that's really cool. You got that experience and really kind of, yeah, I mean, really, you had done, experimental work pretty much your entire life, and then switching over to
Mhm.
DFT is, really kind of round out your area of expertise and your kind of, your skill set. That's really, really cool. But this is kind of what brings us to your research now. So, recently promoted to associate professor. So congratulations on that. I'm sure, that
Thank
can
you.
be
Thank
a
you.
bit, yeah. So, but
Anticlimactic.
we'll transition. Yeah. Oh, is it really?
Well, I'm sure you've
um,
heard this, right? Like you hear like, at least for me, I got like 7 or 8 different like notifications spread out across a year, like, at all these different levels, sort of like notifications that I've been recommended for tenure. So like the process drags out for like so long that by the time it's official, you're like, yeah, big surprise. Like,
I didn't know. I
yeah.
actually didn't know that, but okay. Oh man. Okay. It does seem like a slog then. Um, but so kind of your area of research. So, you kind of do, looking kind of like you've been alluding to throughout this podcast, though, is the idea of catalyst selectivity, but also kind of, really understanding cross coupling methodology and really what's really happening in these elementary steps and these cross coupling reactions. I think is kind of, really an area of that your research group likes to tackle. So I'll kind of hand the floor over to you because I'll kind of, I'll let you, we can kind of dive into each area or each facet of your research group. But, I definitely will let you take the floor here because I really like it, but I like to hear the experts explain it first.
Yeah, I guess I'm not quite sure where to start. Uh, what we've sort of ended up
We can start
doing
with,
isn't, oh, go ahead.
I was gonna say, we could start with like maybe controlling selectivity and catalysis. Like, I don't know if you want to,
Mhm. Yeah, and
go there.
that's definitely become the main theme of my research. Um, I was gonna say, like, it's not exactly any of the things I propose to do in like, my job talks. Like
Mm-hmm.
when applying for jobs, you usually have like 3 proposals. One of them I've never even worked on. The other 2 I've worked
Okay.
on. One of them was okay, like the tantalum stuff that uh, we did some stuff with it, but didn't go too far with it. And then the project that ended up being the one that's become the main focus, like we're not actually doing what I proposed to do. It's just sort of related to what I proposed to do, if that makes sense. So like,
Yeah.
yeah, so we ended up just getting really interested in this issue of selectivity and cross coupling, and it felt like this kind of scenario where you can use a complement of techniques like DFT, as well as experiments to try to understand what's going on with selectivity. So Houk and Schoenebeck had a publication back in like 2010 that was really inspiring, where they had like computationally looked at this chemoselectivity that Fu had reported back in the early 2000s. So Greg Fu had found that, he had these papers showing that you could use tritarbutylphosphine, like really bulky phosphines, right, to get cross coupling of aryl chlorides under mild conditions,
Mm-hmm.
which was really novel at the time. And he had like this one example, or I think a couple examples in that paper of like 4-chlorophenyltriflate, or I think there was another like chloroaryl triflate. So triflates are normally thought of as being more reactive than chlorides. But Fu had found that with tritert-butylphosphine, you get selective cross-coupling of the chloride and not the triflate. So that was kind of opposite of what people would expect.
That is pretty
and
interesting.
then in 2010,
I actually didn't know that, but okay.
Yeah. So in 2010, like Houk and Schoenebeck did these DFT calculations to try to understand where that selectivity was coming from. And so they figured out that it has to do with basically oxidative addition at monoligated versus bis-ligated palladium. So tritert-butylphosphine is so bulky, and you know about bulky phosphines, obviously, so bulky that only one of these can fit onto palladium during oxidative addition, whereas with even a little bit smaller ligands like tricyclohexylphosphine, you can fit two of them on palladium during oxidative addition. And so they basically concluded that mono and bis-ligated palladium have different selectivity preferences for chloride versus triflate. And so I had written this proposal that was basically trying to sort of exploit this idea with like photo switchable ligands where you could kind of switch whether it would be like sort of monodentate versus bidentate. And like, I don't know, it was sort of like an idea related to like if you were doing like cross-coupling polymerization, like being able to sort of switch selectivity in the process. And we didn't really get far on that at all because we just kept sort of finding little other things that were interesting to pursue. Like one of the first things we did was like my students sort of accidentally stumbled on discovering that certain NHC ligands also give this like selectivity preference for chloride over triflate. So we kind of wanted to look into like that concept more broadly. So we did some stuff with NHC ligands there. And then that ended up turning into some other sort of more mechanistic stuff, like looking at how solvent molecules can coordinate to palladium and sort of serve as a second ligand, even when you have a bulky ligand, which can sort of switch your selectivity. And then and then we started getting into site selectivity. So what I mean by that is like where you have two of the same leaving groups, so like two chlorides, but at different positions of the molecule, and trying to understand where site selectivity comes from. And so we because we had found like these bulky NHC ligands give the selectivity for chloride over triflate, we were like, what about with like can they also sort of invert the normal selectivity you would expect with like dichloroheteroarenes? And it turned out that in some cases they can. So that's a direction we started pursuing, like we sort of published some kind of like methodology stuff, but then also a lot of, what really motivates me, and I think my students as well, kind of mechanistic studies, trying to understand where the difference in selectivity comes from. And so that's something we're continuing to work on. We have other substrates, I would say, that we're more excited about being able to switch selectivity. So, like ones that nobody's ever gotten to react at a different site before, and so trying to get that to switch. That stuff we haven't published yet. And then we have some of this has led to just sort of an interest in just fundamentally understanding really what's going on during oxidative addition. So like when you learn about oxidative addition, like if you take an organometallics class, what you learn is if it's an aryl halide, oxidative addition takes place through this like three-centered concerted mechanism, right? So it looks like a triangle, like palladium, carbon, halide. And it turns out that it's more complicated than that. Like that is one possible mechanism, but there's also sort of, it's a little bit of a continuum, but there's sort of a different possible mechanism that looks more like, almost more like a nucleophilic aromatic substitution, where like palladium is not interacting with the halide. It's sort of just like, it's bonded to the carbon and the halide just sort of falls off, like dissociates, so a more polar transition state. And so that was kind of known that there was like this other possible variant, but I would say it was almost like just academic curiosity, like, that there were sort of these two possible variants. But then we started to realize that those two possible variants for the oxidative addition mechanism was relevant to like the changes in site selectivity that we were observing. So that led to like a project that started as a COVID project. Like I started it in 2020, like just stuck at home, just doing a whole bunch of calculations. And then my student, Matt Kenya, took over it. That was basically just trying to do this like large scale computations on oxidative addition mechanisms. Like as you change your leaving group and you change your substrate and you change your ligand and how many ligands are on palladium, like when do you see concerted mechanisms being favored? When do you see these other sort of more SNAR-like mechanisms being favored? And so we've got that one up on Chem Archive, and it's under review right now. But it's really fun to try to figure these things out. And something that I've sort of been inspired by lately is the idea of like sort of collecting different tools in our toolbox to use. So like so far we use DFT calculations, and then otherwise we just do sort of like some catalytic reactions. But we've started to do like heavy atom KIEs, like C13 kinetic isotope effect studies. So my student Matt did that, did some of those studies on this paper that we've got on Chem Archive, which is like such a cool technique. I've always thought KIEs were cool, but like I never really had a chance to do them before, like in grad school or something. And then like heavy atom KIEs, like Singleton's method for getting carbon KIEs is really interesting. And so that sort of let us also distinguish, or at least provide sort of experimental validation for what the computations were saying, like distinguish between when you have a concerted versus this other type of mechanism. So we'll probably be doing more of that in the future as well.
Yeah. I read through your Chem Archives paper and I thoroughly enjoyed it. Right. As I mentioned earlier, like kind of, our group is interested in palladium catalysis. So, understanding these elementary steps and these little nuances is important to me personally. So that's, actually originally it's that paper in it of itself kind of inspired me to reach out to you to have you on, because I thought it was just really cool. But I guess maybe a couple things here. Yeah, I look forward to seeing, to see it like in its full paper, right? So see the whole thing come full circle. But I guess maybe a couple of details here. So you mentioned earlier that, because I'm like kind of looking through some of the publications list, and so solvent coordinations of palladium can induce selectivity differences in oxidative addition. Perhaps maybe you can give us a little bit of insight on that a little bit, like what, if you have an aryl chloride that also contains a triflate. So, what, I don't know if there's any broad banding conclusions or like, that you can kind of a priori think, okay, which one's actually going to cross couple. So I don't know. Hopefully that question makes sense, but.
If you have an aryl chloride and an aryl triflate, unless we're talking about like a really biased sort of substrate, then if you use a bulky ligand, if you use a very bulky phosphine ligand, like tritert-butylphosphine, or I guess there's some even bulkier, it's probably more complicated than what I'm saying. It is more complicated than what I'm saying. You're going to preferentially react at chloride if you can force the situation where you go through 12 electron palladium. And I put that in quotes because, you don't really have like 12 electron palladium just floating around free, but like, so 12 electron palladium absolutely will not, as far as I can tell, react with triflate. Like it's just really a really high energy process to react at triflate, at least compared to reacting at chloride. So you're definitely going to get reaction at chloride. And so I feel like it's a little bit of a canary in a coal mine. If you have a situation with both chloride and triflate reacts preferentially, it's probably a good sign that 14 electron palladium is your active catalyst. So this was sort of like what led us down the solvent coordination study, because like we knew that if palladium has tritert-butylphosphine on it, like you can't have two of those giant phosphines on. So like it should be 12 electron palladium doing oxidative addition. But then we were finding that like in certain solvents, that you were getting reaction at triflate, even though you were using this this bulky phosphine ligand, and it didn't seem to be correlated with solvent polarity, because in very polar solvents like water, like you were still getting reaction at chloride. It was only when you use solvents that have sort of a good coordinating ability, so that have like nitrogen atoms or sulfur atoms that can coordinate. Like oxygen's not usually a good
like
enough
DMSO
kind of
or
ligand.
like
Yep,
DMSO or
DMSO,
ACN or something like that.
acetonitrile, DMF.
Okay.
Those are the ones I can think of in similar solvents. But alcohols, water, we did so sulfolane, which is like a like imagine something like DMSO, but like oxidize the sulfur up one more. So I guess that's a sulfone, right?
Yeah.
So there's no longer a lone pair on sulfur that can coordinate, but it's still a really polar solvent, like similar in polarity to DMSO. Like that, you still get reaction at chloride if you use that sulfolane solvent, but DMSO gives you reaction at triflate. So it seemed like solvent was probably coordinating to palladium, because this trend had to do with coordination ability. So so yeah, basically, I guess we concluded that in coordinating solvents, the active palladium species that does oxidative addition is 14 electron palladium, where that second ligand on palladium is solvent.
Yeah, that's really. I think these little details are super cool, and it's But then the other one I wanted to ask then is, as we kind of wrap up here, is where if you have two chlorines on a pyridine, like a 2,4-dichloropyridine, kind of understanding the site selectivity differences then. So I don't know how easy this is to explain, but is there kind of a general consensus on the different selectivity differences? Like, I don't know if there's a, I don't know how easy that is to explain, but.
So it seems to again come down to kind of the same thing, where if your operative catalyst is 12 electron palladium, or if you can have like again, this is in quotes because it's sort of a cartoon version of what would actually be happening in solution, but if you have enough of a concentration of 12 electron palladium available, so to speak, then you can get reaction at the C4 position. So 12 electron palladium prefers to react at the C4 position, and that's just because that C4, that carbon 4, like has a larger LUMO coefficient, or at least that's what we think is the reason. So like when palladium comes in to react with sort of the pi system, or react with that pi star system, I should say, it can get a stronger interaction at the C4 site. Like it can donate into the C4 site better than the C2 site. But if you have 14 electron palladium, palladium's HOMO has a different symmetry. It has pi symmetry now, which means it can actually interact with like 2 atoms of the LUMO of 2,4-dichloropyridine. So it doesn't really care about which atom has a larger LUMO coefficient, because it can interact with like 2 atoms, if that makes sense. So it then prefers to react at carbon number 2, as well as the sort of adjacent nitrogen. And then it preferentially reacts at carbon 2 because that carbon chloride bond is weaker, in particular when it goes through this SN-like mechanism, this nucleophilic displacement mechanism, where chloride is just kind of spontaneously leaving. Yeah, I don't know if that helps, but
it makes sense to me. Hopefully the viewers have a little good sense of organometallics, because this will be complicated for people that don't really know that. But listen, that's how it goes, right? I mean, we tried our best here to explain it, but it's explaining organometallics can be a little difficult, but that's okay. This is all in good fun. Yeah, I like it. Hopefully this also just does encourage people to actually go read the papers too. So hopefully you get a little inspiration there. But with that, Sharon, I want to thank you so much for having on the podcast today. It was such a delight talking with you and sharing with your experiences, and hearing about your chemistry was really just awesome. I really look forward to your future publications, and yeah, just thank you. And
thank you.
I don't think the viewers don't know this, but you are over in Europe right now, traveling.
Yes.
Given, I assume
that's why the air is so clean.
Are you there on vacation? Okay. Wow.
I don't know
Okay,
if you
this
call it
little diss.
vacation, but working remotely. Yeah. Yeah,
Working
my
remotely.
husband
Yeah.
is Austrian, so we are in Austria right now. My 3-year-old is at his
Okay.
grandparents' house right now, during the day while we work from home, temporary home. Yeah,
Yeah. Austria, man, that is beautiful country.
it is.
That's so
Yeah.
cool that you're over there right now. But with that, viewers, thank you for listening to another episode. And we'll see you on the next one.
Thank you.